So, anyways, we are ready for the second talk. So Fernando Herrera, who is a postdoc here at IMPA, will update us on analytic properties of automorphic L series by its integral kernel.
Okay. So first, I would like to say thanks for the opportunity to give this talk in this workshop. As you said, I'm doing a postdoc here at IMPA, so this is a perfect situation to meet people doing analytic number theory in Brazil, Rio de Janeiro, or abroad. Okay. Okay. Okay, but the idea of this talk is about a specific kind of automorphic form. It is called Siegel forms. One can see this automorphic form like a generalization of the modular forms, and the objects have a Fourier coefficient, so they have a family of numbers, complex numbers. So with them, you can consider a Dirichlet series associated with the object. Okay. The classical way to obtain it is a complex series. I'm going to say everything with the definition and so on. But the classical way to obtain the analytic continuation and the functional equation of this series is taking the Mellin transform. And it is the same way when you take a modular form, Caspidad modular form, and you take the Mellin transform of the Fourier expansion, and you obtain a gamma function times the L series, the Dirichlet series. So in the case of the Siegel-Cas form, the idea is the same. This is the classical way to obtain analytic continuation and functional equation. In this talk, my idea is to tell you another way to obtain the same analytic properties, and is using the integral kernel associated with the Dirichlet series. Okay, so with the talk in the first part, I'm going to define a Siegel-Cas form and so on. Okay. So Hn is the Siegel half space of degree n. The symplectic group of degree n is this set. Okay. A, B, C, D are n by n of the matrices. And the symplectic group acts on this space in this way. So you have any element in Hn, any matrix in the symplectic group, and you do AC plus B times CC plus D, the inverse. Okay? It can be proved for any CD lower blocks for the symplectic element. This is always an invertible element. Okay? So this action, I mean the group on this set, gives another action in the set of the functions where the domain is Hn to the complex numbers. In this way, so for any function from Hn to C to the complex numbers, K is an even integer. So the matrix is acting on the function, so it's another function, and the function is this one. Okay? The determinant of the same factor here to the minus K times the function on MC, where MC is this. Okay? So the Siegel-Cas forms of degree n and weight k are holomorphic functions, which are invariant under the action of this group. This is the first point. And the second one, they have a Fourier expansion where the elements are positive. Okay? So it is important to get that when you have any Siegel-Cas form, you have a family of numbers, AT. For any T in Jn, you have a complex number. Okay? It can be proved the order of AT is the determinant of T to the K half. Okay? Okay, but the set of these functions is a vector space, a finite dimensional vector space. Here you have in a product in this space, okay? This is a differential invariant under the action of the symplectic group on the space. Okay. Okay. So if take any Siegel-Cas form for degree n and weight k, you take the Fourier expansion and take its Fourier coefficient and consider the Dirichlet series. Epsilon t is just the order of the stabilizer of the action on t, okay? So it is just a natural number. As I told you, the order of this is the determinant of t to the power k half. So this is a convergent series. It's a holomorphic series in the variable s when the real part of s is greater than k half plus 1. Okay? So when you have a series like this, it is normal to study if it has analytic continuation and some functional equations, okay, to the other side of the complex plane, okay? So in this case, I mean, this series is, if you consider the complex plane, here is k half plus 1. So this series is a holomorphic series here. Okay? Maybe it's m plus k, okay? Okay. In the cases of Jacobi forms, Siegel forms, modular forms, and so on, if they have a Fourier coefficient, you can consider the Dirichlet series. So in the case when you are considering the Siegel forms, this series is also called the Kecher-Mass series. Okay? Okay. Let me tell you the easiest case is when n is equal to 1. So in this case, when the Siegel-Cas forms are exactly the modular forms. In the first Siegel space is exactly H1. So it is only the complex numbers such that the imaginary part is greater than 0. The first group, SP1, is exactly the group SL2C. Okay, so this group is acting on H1 for the Mobius transforms like this. Okay, so if the matrix in SL2C is ABCD, and C is an element in H1, so this is the action, okay? So the Siegel-Kapp's forms for degree 1 are exactly the the modular Kapp's forms of weight K. So are holomorphic functions from H1 to complex numbers. They satisfy this equality for any metrics. The Fourier series can be written in this way. Okay? Here, the element who are indexed is the natural number. So the series is this series. It is a well-known series, I think. At least when you consider a modular Kapp's form. Yeah. Okay. Okay. Mass in 1971 showed the Kecher-Mass series. Okay, the first point I just told you defines a holomorphic function in this region. Sorry. Only well, in the drawing. And the two are not obvious statements are the series has an analytic continuation to the complex plane and satisfies a functional equation. Okay. But the proof is the same idea of Hecke's idea. I mean, taking a generalized Mellin transform of the Fourier series, and then you can obtain the product of the gamma factors times the Dirichlet series. And then the Mellin transform is an integral. You can split in some way that the matrices are holomorphic in the whole space. So you can define the analytic continuation using this equality. Okay, it's the same idea if you consider the case n equal to 1. Okay. Okay, so the idea, as I told you, this is the classical way. So I would like to comment some works using other way, the integral kernel. Okay. Okay, let me define the integral kernel. If you consider now a complex number where the Dirichlet series converges, for example, in this case, so here it's important to note the S is fixed, and I consider the map from the vector space to the field. I take a function, take its Fourier coefficient, and consider the Kecher-Mass series, and then I evaluate at S. So it is a complex number. It is not hard to see if this is a linear function. So I have a linear function in a vector space. So for using a linear algebra, there exists a vector in the vector space such that the linear map can be written as in a product between the vector and an element in the vector space. So for any S, there exists an omega of S such that this equality holds for any F here. And this element is the integral kernel associated with df. So the idea in this talk is use always this equality. So in the following works I'm going to show you, the idea is I take a very specific Dirichlet series, and they are going to find the integral kernel of the Dirichlet series and study the analytic continuation and functional equation of omega. And then using that it has the analytic properties to obtain the whole expression has the same properties. Because here, I mean, it is an integral. So if you obtain those things, so you can define the Dirichlet series in the other side of the space using this equality. Okay. Okay. So let me show the first and easy. Ah, okay. Sorry.
The centrifugal kernel is hospital. Does it arise the holomorphic projection of an Eisenstein series?
Sorry.
The kernel, the centrifugal kernel is hospital.
Yeah. It has to be cuspidal.
Yeah, but does it arise as the holomorphic projection of some Eisenstein series?
I mean, if you have, are you considering the F, the Eisenstein series?
Where are the constructions in the literature? Where there's, like, for instance, in Greg's Conan Zagier, you have an Eisenstein series, you take the holomorphic projection, which will be plus form of balance. It gives the kernel function in the same way.
But I'm not sure if they satisfy the same equality. Omega is a cuspidal function for any S. Okay. Oh, okay. Okay. The first case, when n is equal to 1, go and consider the integral kernel for. So when n is equal to 1, you have this Dirichlet series. The integral kernel that Cohen found it was this. So here S is the complex number and C is an element in H1. Okay, so this element satisfies, but this is omega. Okay, so this element satisfies this equality. Sorry. Okay. But Cohen only considered and found the integral kernel for a very specific the values actually just integer some values, okay? And then Diamantis and O'Sullivan consider the same integral kernel from Cohen, and work for, and then obtain the analytic continuation to the integral kernel for S, to the complex plane, okay? They prove it has a functional equation. So, as this element satisfies functional equation, and if you define this in this side, like this, you obtain the same analytic, the same functional equation for df. Okay, but this is the technical issues. If you take n equal to 1, the group is this one, and the Fourier series is this one, okay? Okay, for any n was made by Conner and Sengupta, and in this case, the group is the whole symplectic group, The Fourier series is this one. So this is the Kerr-Mass series I showed you. Okay. The integral kernel in this case is this expression. G0n is a very specific subgroup of the symplectic group. Okay. So if you see, this is a power function. So the region where this series converges is small. Okay. So the idea behind to obtain the analytic continuation of functional equation using the identity is to obtain this function has an analytic continuation, the integral kernel. And he has some functional equation, maybe one or some more, maybe, okay? Okay. Okay, the third work was made by Yves Martin. He was my advisor. He considered the case n equal to 2 with a twist. The twist was the Eisenstein zeta function. This is for the definition. So the Dirichlet that he studied was this one, okay? So here you have the Fourier coefficient, the epsilon t, it's just a natural number for any t. This is the twist, and this is the other factor. So this is a Dirichlet series twisted by this function, okay? And he obtained the same. He studied the integral kernel associated with this Dirichlet series. So this series is the same series I showed you. And this was the integral kernel who he found. Okay? And Q is a power function. This is the definition of Q. This issue is about, in the other cases, the Dirichlet series has only one, the variable, only one. So they obtain only one functional equation, and the order 2. I mean, if you use the functional equation and use again, you obtain the same function, okay? For Martin, he has two variables, S and double B, and he obtained two functional equations. The order of them are 2, and they commute. So the group of the functional equation in his case was the Klein group. Okay. So in the other cases is the cyclic group of degree 2. You have only 2 elements for n equal to 1 and any n. For Martin was a group of 4 elements. And okay, here is my work. My idea was consider a generalization of this series. Okay. So I consider the Epstein zeta series can be written as the Selberg-Eisenstein series of degree 2. This series can be defined for any n. So I consider the Selberg-Eisenstein series of degree 3 and consider the Dirichlet series twist by this function, okay? It is not hard to see. Here I have the determinant of t to the minus u, but you can put inside of this function. So this is a Dirichlet series, okay? So in another way, if you see this identity, the series studied by Martin, you can change the Einstein zeta function for the Einstein-Selber series here. Oh, sorry, here. Okay. Okay. So, I consider this series, and my idea was the same: try to find the integral kernel for this series, trying to prove the integral series has an analytic continuation and functional equation, and then using the identity, obtain that the Dirichlet series satisfies the same properties. Okay. So here is the Dirichlet series. This is the integral kernel that I found. And in my case, I have more functional equations. Some of them don't commute. And this group has 12 elements, and it is isomorphic to the diederal of degree 12. And P is some power function in this space. But this is all I wanted to tell you. Thank you.